So thanks for coming. Today I'm going to start, I'm really not quite getting into material science, but about some tools that we developed for modeling to help us analyze our work with RCA better and use in conjunction with all of the other tools that we're using as we use RCA. So just to get everybody on the same page of RCA, right? RCA is crushed or demolished concrete that has been turned into aggregate size pieces. It goes through a process of cleaning and crushing, and that process can impact how much of the paste is still left on the aggregate and how much maybe there's fractures in that paste, things like that. So if you didn't know what RCA is, now you do. Concrete made with RCA is recycled concrete, aggregate concrete, or RCAC. And when we talk about RCA, it's a byproduct of crushed concrete, and so it's a multi-phase material, right? So we have our original aggregates that were used in that system, both fine and coarse. We have the adhered mortar or the original paste from the parent concrete, but then we also have the ITZs between those as well. And so when you start looking at all of the components that go into performance at the mesoscale level of concrete, you have to consider that the ITZ of the recycled aggregate to the new paste is different from the ITZ between the old aggregate and the old paste. So there's all of these different components to start thinking about. You can't just sort of use a single value for your aggregate anymore in your modeling tools. Recycled concrete aggregate has a number of things that are pretty different from natural aggregates, right? So we typically have high porosity and absorption capacity. The amount of adhered mortar on that aggregate is going to be pretty variable depending on how you process it, what the quality of the parent concrete was, and it's usually a relatively low, much lower density depending on how much natural aggregate is really in there. And that being said, because of all of that, these products are pretty variable because you're not getting most of the time you're not getting all of your waste concrete from a single source, a single mix design. You end up with stockpiles that are different. So why are we using this, right? RCA is useful for cost, it's useful for sustainability. We're even seeing some indications where it's really helpful for shrinkage cracking resistance in some cases and things like that. I'm not going to get into that today, but there's a number of reasons why we might start using this as an aggregate in concrete. I just want to go over the CO2 benefits, since this is sort of the key item for sustainability at the moment, is that people are really worried about embodied carbon. Recycled concrete does not typically give you a good return on investment for reducing your carbon. The emissions pound per pound between an RCA aggregate and a natural aggregate are pretty similar. The only time that you are seeing good impacts is when you start looking at travel distance, right? So if your construction site that you're demolishing to the plant where you're processing your RCA back to the new construction site is a lower amount of transportation than getting natural aggregates, that's really where we start to see CO2 benefits. But otherwise, you know, if that distance is relatively the same, you're not really going to get much CO2 benefit. Your benefit really is on other aspects such as, you know, reduction in mining and landfill reduction, things like that. So when we do work with RCA, there's a lot of challenges to this. So I'm going to say this many times, right? It's a highly variable material. And when we make concrete, we can't create aggregates in a specific orientation. We can't put the adhered mortar in a specific place. We can't even guarantee exactly how much adhered mortar is going to be there. We could get an average number for all of our aggregate, but it's really difficult to know what each aggregate has attached to it. And also, when we get material from stockpiles, we're looking at stockpiles of multiple sources. And so unless you are really, really good about your sampling of that pile, standard sampling techniques are not going to give you a good average value for the quality of that concrete, right? So because the piles, as you see here, get they're not mixed up. It's not a homogeneous pile of aggregates. You've got pieces, full piles of different systems all over the place. So the reason why this is important, right, is when we start looking at how we design concrete mixtures, our traditional process with normal aggregates, we've got a lot of well-engineered systems these days where we have quite a bit of empirical data that we can then use to move forward with creating mixtures that we then double check. We don't have that same information with recycled concrete aggregate, and because we can't control things like orientation and amount of adhered mortar, which are incredibly impactful on properties, it makes it very difficult for us to develop those same engineered relationships. So because of this, we need to use modeling to expand our capabilities to look at those, because when we use modeling, we can theoretically orient an aggregate in any direction we want. We can put the adhered mortar in any place that we want, and so we can start to look at real impacts. So for example, it's long been said that systems with RCA have worse corrosion protection, but the results in the field or in literature is actually all over the place. But when you actually look at them, it's all over the place because you've got systems with all these different adhered mortar contents. You don't know where the adhered mortar is, and I'll give an example at the end here, but basically where the adhered mortar is in relative to a reinforcing bar is incredibly impactful to how fast corrosion might start, right? Because chlorides can move through the adhered mortar, but they can't move through the aggregate. So these are things that are really important for us to understand. So when you start looking at modeling though, most systems for concrete, a lot of them are starting with spherical aggregates, right? So shape is not considered. They're smeared properties, so the entire aggregate has one property assigned to it. We know with RCA that's different. We've seen attempts in literature to then make portions of those spherical aggregates a slightly different property so that you can start to consider the adhered mortar properties versus the natural aggregate properties, but we're still not looking at a realistic distribution of aggregates, realistic aggregate shapes. So then the next step that we moved forward with was people started doing image analysis where they'd slice a piece of concrete, take an image of it, and then we could upload that into a system and use an algorithm to essentially digitize that and put a mesh on it and then assign properties to those different meshes. And this was really helpful because we could start to look at some realistic gradations, realistic distributions, realistic shapes. But when you're using an image as your base, you still can't sort of have a random generation of properties. You can't start doing good Monte Carlo simulations. You can't change the orientation of something to see the impact of that in the exact same system. So that starts to make it difficult. But with this, we are able to look at some things like, okay, if we increase the overall adhered mortar content on every aggregate, what changes do we start seeing in compressive response, tensile response? And so that was a good starting point for us. But again, we're still unable to capture all those other dynamic items, which we assume are playing a really difficult role, or a really important role. So what we did was we worked to develop a system to create a random aggregate generator tool that could produce realistically shaped aggregates that you could then also have realistically distributed adhered mortar on those aggregates. And so what we start with is we want to define a region for our aggregate to be in. And if you want to work with a crushed aggregate, that starting space is a square. If you're working with a gravel that is a smooth river gravel, you start with a circle. You then populate that space with dots. Just fill it up with a random number of dots. And then you perform what's called the convex hull algorithm, where it takes the outer edges and connects those dots. And so when you start with a circle, you end up with a more rounded aggregate. When you start with a square or a rectangle, you end up with a more crushed-like aggregate space. We then can continue to use that to look at all of these shapes, but we can also use that same dot matrix to start adding our adhered mortar, right? So now we can connect different dots to change the total amount of adhered mortar on that aggregate while keeping the aggregate the exact same shape, the exact same orientation. We can also just twist that aggregate if we want to. So we have this coming through, we can build this up. Again, it's not perfect, right? Because that adhered mortar is still a relatively straight line. That's something that we're working on. We're also working on how to turn this into 3D, but this has been a really good start for us. So then once you have the ability to create the individual aggregate, you also want to distribute them. So you build a raster of your of the sample that you're going to test in the model, and you start placing those aggregates into that system. And so basically, we created an algorithm that that doesn't overlap the aggregates, and then you can also tell it, this is the gradation that I want, this is the total aggregate content that there needs to be, and that algorithm will essentially randomly generate those aggregates in those proportions within that space. We then can take that and assign colors to all of the different pieces and assign then property values to the new adhered mortar, the original aggregate, the original parent aggregate, the old adhered mortar, and even at those barriers assigning different properties to the ITZs. So we can start to look at the impact of ITZ as well in this system. So this is a real-time video of how fast it takes to actually create that with the system that we were using. So this was all built in MATLAB, and then we were importing this into a Diana model, and in Diana we were then assigning all of these values based off of the colors associated with it. So here's an example of sort of the variation that we could do. We've got on one side, we've got increasing aggregate ratio. So on the left, we're seeing increasing amounts of aggregates. On the top, we're going from left to right, increasing the amount of adhered mortar on that system. And we can run those many, many times so we can get many different generations of these aggregates with those same values. And once we get that, we can start doing all of our Monte Carlo simulations. We can start looking at varying the ITZs from one property to another and see how much is this impactful on the mechanical properties. And so we have a paper out where we looked at really what is the potential variability that we might see in a standard concrete mix when using RCA from a stockpile. And so this has been a really valuable tool for us. What we wanted to do then is how can we actually apply this model in a more, for durability and for corrosion. So we really wanted to look at chloride distribution and how aggregate shape and size impacted that. And so we are able to generate many of these random aggregate places. And then we have a model that is set up where we've connected Diana with COMSOL so that we can input the mechanical properties. It will put it under some stress. It'll go into COMSOL. It'll measure how much chloride is moving through on different time steps. And then at the end of the day, we get both mechanical damage and chloride ingress into our system. And so this is just one example of what we were able to do. And so we were able to look at the actual impacts on this. And so at the end of the day, we've got different adhered mortar contents. And what we see is more adhered mortar, we get more chlorides further. But also what we saw is that if the adhered mortar was in the path of the reinforcement, corrosion would start faster. If the aggregate was oriented a different way or there was less adhered mortar just in that path, even with the same amount of adhered mortar overall, you'd get slower corrosion. So those were things that really helped us to prove out what we were seeing empirically with other research. So these tools were really important to help us create some more realistic systems with recycled materials, which are quite different than our natural materials. And we can combine them with existing modeling systems to use all of the data that we're getting from the rest of our scientific discovery to put in these new types of materials and get enough data that we can look at variability and things like that. So that was a really quick overview of what we did, but I'll take any questions.